Chapter 1 practice test number 13. Go and read all this, absorb it. You're going to need your balanced reaction. They do think you know that nitrate's -1, and it would help to know that silver is +1 always. In the real question, they'd probably have a clue that that's +1, because you are not given an ion table, and the metal ions you're probably not exactly expected to know if they're not in a column 1 or column 2 kind of thing. So what you have here is a limiting reactant problem, although it may not look like it. You have 1 mole of each of these, but they don't react in a 1-to-1 ratio. They react in a 2-to-1. So if you have 1 mole of this, you need 2 moles of that, but you don't have it. The thing you don't have enough of is your limiting reactant. It's the one you run out of. So we'll use up all the silver nitrate. All the silver ends up here. All the silver is in the solid. Where did everything else go? Well, all the K ended up here, all the NO3 ended up here, except they're not really in the same ratio, because 1 mole of this whole salt gives 2 moles of K+, and it's left in solution because it's a super soluble. 1 mole of this gives 1 mole of the nitrate, and it's really tempting to say, no, look, there are 2 of them. That's the ratio of the recipe. That's not how much you have on hand. You had 1 mole of this. So you had 1 mole of nitrate. There's 1 mole of nitrate left in solution. So it takes 2 to react with 1 of these. So you react half as much as whatever you have of this. If you have 1 mole of this, you react with half a mole of this. So half of your 1 mole of this gets put into the solid, and half of it is unreacted. Half of the sulfur ion is unreacted, which means half of the 1 mole is left in solution. Now about the diagrams themselves, this has 2 supersolubles in its precipitate, so that is called officially dumb. This has the wrong answer, so that is out. These 2 have the correct formula for the precipitate, but let's look at this. There's no sulfur in this solution. So the ratio would be 2 to 1 to 1/2, or look, 4 to 2 to 1. In 14, I know that HF is not one of our classic strong acids, and it does not automatically 100% dissociate and ionize when it hits water. However, the part that's going to react with that is the part that presumably dissociated, and this is going to happen pretty quick, because all the part that does manage to dissolve is going to react with the part of this that dissolved, and they're going to form water. And nature loves to make water and carbon dioxide, so this is going to meet up and make that real nicely. And by Le Chatelier's principle, if you keep removing the reactant, the product, of this dissolving and that dissolving, they keep proceeding toward creating more product. And that product of H plus and OH minus keeps making water. Also, the product of the dissociation of F minus and Mg plus 2 keep making this product. Now, this presumably dissolves a tiny bit. Everything dissolves a tiny bit, but does it dissolve enough to matter here? No. You're going to make a solid very definitely, because it doesn't have any of my super solubles in it. And so the net ionic equation includes everything, because everything changed. Everything over here was aqueous, and water is not aqueous. It's a liquid. And that does not count as aqueous. Water is water. It's not dissolved in water. And so your net ionic equation includes everything. So if you take hydrogen peroxide and you make it into water and O2, which is what's happening under your bathroom sink, if you leave the cap just a little bit loose, the oxygen gas keeps escaping, and by Le Chatelier's principle, it keeps proceeding toward making the products, and you end up with just water, and you've leaked the oxygen gas out of the bottle. But is this a chemical or physical change? Well, it's chemical. You have different chemicals than when you ended, but a better answer, and explain how you know. Bonds are broken and created. One of these O's broke off, and it made a new bond with that. Weirdly enough, S8 is one of the elemental states of sulfur, so that's a charge 0. Also, it's by itself, so that's a giant clue that that's its elemental state. And sulfur is not one of our 8 diatomic elements, is it? Out of these three, which is most likely to change its oxidation state? Well, it sure isn't sodium, and it's not oxygen. This isn't a peroxide. So by all math logic, if that's -2, then we have -6. The answer here, well, what is the answer on S2O3? How should I know? Well, it's attached to 2 plus 1s. The answer on this is -2. If the total minuses here is -6, then the answer over here must be +4. The oxidation state total, and it took 2 of them to do it, so the oxidation state here of sulfur is +2. And I will point out that really weirdly, and I don't think they would do this on a real test, but theoretically at least, it is possible to get a fractional oxidation state. I assume there's some sort of resonance structure going on in here. I didn't diagram it out or look it up. And by the math, you get 5.5 oxidation state from sulfur. So the highest oxidation state is positive 5.5. By highest, they mean most positive. This is the elemental state of copper because it's solid. The oxidation state of silver is +1 because silver is only +1 anyway. Plus, it's attached to a -1, so that helps you out if you forgot. Look, that's solid silver. Solid metals are in their elemental state, and their charge and oxidation state is 0. So this went from 0 to +2, and because it's attached to 2 minus 1s. And this went from +1 to 0. So what happened chemically? Well, electrons were exchanged. Copper went from 0 to +2, so it lost electrons, 2 each. And silver went from +1 to 0. It gained an electron, 1 each, but there were 2 of them. Remember, for every time this runs, there were 2 silvers used. Now, what would you see? You'd see silver solid. Now, I will point out, and you can probably find this on YouTube, but when you make this, it doesn't come in a lump. And I know they draw it sort of as a lump in those diagrams that we just talked about on 13. But realistically, this happens throughout the solution in very tiny amounts each. And they do sort of clump together, but what you get is a powder, not a solid lump of metal by any means. And in fact, sometimes it's pretty hard to identify what's going on. And you get stuff like copper looks red when it's a powder. And copper's not red. Copper is a new penny, I know. But for some reason, if you make it in extremely small amounts and disperse it, as and it's a powder, it looks kind of reddish. So I don't recall what color this is going to be, but it's not going to be shiny and silver. But you'll see a silver powder. And I looked this up. I'm not expecting you to know this. The test does not expect you to know this. I looked up the color of a copper +2 solution. It turns out it's blue. They wouldn't ask that in that manner. So you ran this reaction, take a look at that, and if you add this much potassium permanganate, you end up with something clear. And this much, and this much, and this much. And finally, if you run it adding this much, it's pink. Well, why was there no color formed the first time? Well, if you got a different result as you added more and more and more, this was your limiting reactant. You kept running out of this, and there was none left over. Finally, you managed to add enough that there was some left over, and apparently permanganate ion is pink. I'm hoping I don't really have to walk through all the oxidation states on this. Double check me, but I think that's right. And so the iron went from +2 to +3, which means it lost electrons. And the manganese went from +7 to +2, which means it gained electrons.